A black hole isn't pulling you in. You're falling because space-time itself has bent so sharply that away no longer exists. This is where physics breaks, time slows, light orbits itself, and Einstein's gravity fights quantum mechanics with no clear winner. But here's the unsettling part. A black hole might not be an ending. It could be a doorway. If you want science that goes deep, follow the channel. Now, let's walk to the edge. Gravity is the most familiar force in your life. You don't need to think about it to know how it behaves. It pulls you downward when you wake up. It makes a ball fall the moment you let go. It shapes the way rivers flow, how planets orbit, how your feet stay on the ground. After a lifetime of living under its influence, your intuition treats gravity as a simple, predictable, almost boring part of reality. But that intuition is profoundly incomplete. The gravity you know is only the mildest version of something far more powerful, far more flexible, and far stranger than the everyday world reveals. The gentle downward pull you experience is just one expression of gravity, a faint echo of a deeper, more fundamental phenomenon. And if you amplify that phenomenon far enough, if you let gravity operate without the limits of ordinary matter, it eventually reshapes reality so drastically that light itself becomes trapped. That extreme state is a black hole. Understanding a black hole begins with understanding gravity, not as a pull, but as a geometry. For centuries, gravity was thought of as a force acting between objects, an invisible thread connecting masses across space. But in the early 20th century, Einstein rewrote this idea entirely. In his description, gravity is not something exerted by objects. It is the shape of space-time itself. Mass tells space-time how to curve, and space-time tells objects how to move. Everything, planets, rocks, photons, even time, follows these curves. At Earth's scale, these curves are subtle. They bend just enough for apples to fall and the moon to orbit, but not enough for your senses to feel the curvature directly. You live in a region of space-time that feels flat simply because Earth is too small to warp space-time dramatically. Your intuition was built inside this mild environment, so you naturally treat straight lines, up and down, and the flow of time as fixed aspects of reality. But none of those things are fixed. They are simply gentle approximations of a deeper truth. Gravity is the architecture beneath motion, light, and time. And black holes are the places where that architecture reaches completion. To see this, imagine light, the fastest, most uncompromising traveler in the universe. For most of history, scientists assumed nothing interfered with its journey. Light seemed unbending, eternal, perfectly straight. But during a solar eclipse in 1919, astronomers measured the positions of stars whose light passed near the sun. Those stars appeared displaced. Their light had curved. This tiny shift was enough to show that space-time itself acted like a lens, bending the path of light even though light had no mass. This bending was small near the sun, but profound in meaning. It implied that if you placed enough mass into a small enough space, the curvature could become so sharp that all paths turned inward. Light would no longer have a route that led outward. You would not trap light using walls or matter. You would trap it using geometry. This is the first essential truth about black holes. A black hole is simply gravity operating at full strength. Once you understand this, black holes stop being mysterious objects and become the ultimate expression of something familiar. Every bending of light, every slowing of time, every curved trajectory you've ever seen is a preview, a hint, of what a black hole is doing on a grander scale. Time, too, is shaped by gravity. A clock placed at Earth's surface ticks slightly slower than one on a mountain. The difference is tiny, but measurable. GPS satellites rely on correcting for this effect every moment. Without compensating for gravity's influence on time, your phone's navigation would drift kilometers off course. Here on Earth, gravity slows time gently. Near a massive star, the effect becomes stronger. Near a black hole, it becomes overwhelming. Picture two clocks, one far from a black hole, the other drifting closer. To the distant observer, the falling clock appears to run slower and slower. At first the delay is slight, then it becomes noticeable, then dramatic. Eventually, as the clock nears the region where a black hole's horizon will form, it seems to almost freeze. Time itself stretches into near immobility. But for the clock falling into the gravitational well, nothing unusual happens. It ticks at its normal pace. Its experience of time is unchanged. This difference in perspectives is not an illusion, it is a structural feature of space-time. Gravity reshapes time differently for different observers, and in black holes, that reshaping becomes so extreme that time and space trade roles entirely once you cross the horizon. This is why understanding gravity is the first step toward understanding black holes. Every effect a black hole exhibits is already present around you, just in miniature. Gravity bending light near the sun is the beginning of how light becomes trapped near a black hole. Gravity slowing time on Earth is the beginning of how time nearly stops outside a black hole. Even the way objects fall is a hint. Drop something on Earth and it speeds up as it descends. But imagine a place where the descent never stops, where the geometry forces everything to move inward no matter what. Imagine the curvature becoming so severe that falling is no longer something you choose, but something the universe defines as your future. That place, too, is part of a black hole's structure. To understand how close you already are to black hole behavior, consider something even more startling. Photons, the particles of light themselves, can orbit a black hole. This orbit doesn't require mirrors or atmosphere or complicated machinery. It happens purely because space-time is curved so strongly that the straight-line path of light becomes a circle. There exists a region around every black hole where light can spin endlessly. This region is called the photon sphere. The photon sphere is not the black hole itself. It is outside the region where escape becomes impossible, but it is the first unmistakable fingerprint of black hole geometry. It's the transition zone where gravity begins to reveal just how flexible reality truly is. If light can orbit, then the usual notions of direction are dissolving. Straight lines no longer exist in the way you imagine, and the world you trust, where space behaves like a flat stage and time flows evenly, begins to unravel as you approach this boundary. This is why black holes are not exotic. They are simply the natural outcome of gravity continuing its work without limits. If you've ever watched an object fall, or seen the sun bend starlight, or used GPS on your phone, you've already interacted with the early versions of the physics that creates black holes. Black holes are not separate from these effects. They are these effects, escalated to their ultimate form. Now, imagine amplifying gravity again. Make curvature steeper, slow time further, bend light more dramatically. Continue until every possible path from a region of space-time leads inward. Continue until even light cannot escape, not because it is weak, but because no route takes it outward. That is the boundary of a black hole, the event horizon, and it forms when gravity fully takes control of space-time. But even here, we are only at the beginning of what black holes truly are. The horizon is not the black hole's interior. It is merely its edge. Inside, the rules of space-time depart from the familiar entirely. Space collapses inward, time funnels downward, forces magnify, directions dissolve. But all of that follows from the same principle that explains why an apple falls and why planets orbit the sun. Gravity curves space-time. This chapter has one purpose: to dismantle the intuition that made you believe gravity is just a pull. To prepare you for the idea that black holes are not strange objects. They are gravity's natural destination. They are the places where the quiet bending of light and time becomes so strong that the universe changes shape. And now that you have seen the early signatures of this transformation, bending light, stretching time, looping photons, the next question becomes inescapable. What kind of cosmic event can produce such a place? A black hole begins its life not as a monster, but as a star, no different from the countless points of light scattered across the night sky. For most of its existence, a star is defined by balance. Deep in its core, nuclear fusion pushes outward, releasing light and heat. Gravity, always patient, pulls inward. These two forces maintain a truce so stable that a star can shine for billions of years without noticeable change. Seen from afar, a star appears eternal. Its glow is steady, its presence reassuring. But that stability hides a countdown. Every second a star burns, it moves closer to a moment when gravity will no longer be opposed. The beginning of the end arrives quietly. Hydrogen, the simplest and most abundant element in the universe, begins to run low in the star's core. Fusion of hydrogen into helium is what keeps the core hot enough to resist gravity. When hydrogen runs out, that outward pressure falters. The core cools, contracts, and becomes heavier. Gravity tightens its grip. In response, the star's outer layers expand, trying to compensate for the shrinking core. The star may become a red giant, swelling to enormous size, but the core continues to collapse. The cycle repeats as the star fuses helium into heavier elements, but each stage is shorter-lived. Eventually, the star forms iron, the element that stops the entire cycle in its tracks. Iron cannot produce energy through fusion. It absorbs more energy than it releases. And without energy to push outward, gravity is left unopposed. This is when collapse becomes inevitable. It happens not over millennia, not even over years, but in a fraction of a second. The core suddenly gives way under its own weight. The outer layers plummet inward, reaching unimaginable speeds. The collapse accelerates as the core becomes denser, hotter, and more compact. The gravitational pressure becomes fierce. Electrons are forced into protons, creating neutrons. This process releases an enormous amount of energy, briefly halting the collapse. The infalling material smashes into the stiffening neutron-rich core and rebounds outward. That rebound can trigger a supernova, one of the most dramatic events in the universe, bright enough to outshine an entire galaxy. But the explosion is only half the story. The real transformation happens in the core that remains behind. To understand how extreme this collapse is, consider something familiar: Earth. If you compressed Earth to the size of a marble, its density would rise dramatically. The curvature of space-time around it would deepen, and time at its surface would slow down. But now continue. Compress it further, to the size of a grain of rice, then a grain of sand. Soon you reach densities that no earthly material can withstand. The atoms themselves would collapse under pressure. And yet, even this thought experiment is gentle compared to what happens in a collapsing star. The core of a massive star reaches densities that defy comparison. A teaspoon of neutron star matter weighs billions of tons. The star's structure is crushed into a sphere only a few kilometers across, smaller than a city. But even neutron degeneracy pressure, the quantum mechanical force that keeps neutrons from occupying the same state, cannot resist gravity forever. If the original star was massive enough, gravity overwhelms even this last line of defense. The neutron core collapses further still. As it falls, the collapse becomes unstoppable. No known force in the universe can resist gravity at these densities. Matter can no longer behave as matter. It is no longer meaningful to speak of atoms, nuclei, or even neutrons. Everything is drawn inward by space-time collapsing under its own weight. The geometry of the universe buckles. And at the center of this collapse, something new begins to take shape. Not a material object, not a surface or a core, but a region of space-time where the curvature becomes so steep that escape is impossible. This is the birth of a black hole. But how do we know this actually happens? The universe has shown us. One of the clearest examples is Cygnus X1, discovered in the 1960s. Astronomers observed a bright blue star wobbling, as if tugged by an invisible companion. That companion emitted powerful X-rays, produced by gas heated to incredible temperatures as it spiraled inward. Yet the object itself emitted no light. Weak neutron stars, white dwarfs, dying suns, none of them matched the mass required to explain the star's motion. The only explanation that fit the data was a collapsed stellar core, a black hole. Another case is HR 6819, nicknamed the Unicorn. It appeared to be a binary star system, but only one star was visible. The other object had too much mass to be a planet, too little light to be a star, and too little activity to be a neutron star. It didn't glow, pulse, or flicker. It simply bent the orbit of the visible star with silent gravitational authority. The best explanation was again a black hole, formed from the collapse of a once massive star. No explosion had been seen. No supernova had marked its death. It was a black hole born in silence. And that silence turns out to be common. Not all massive stars end in brilliant supernovae. Some collapse inward so quickly and so completely that no energy escapes to trigger an explosion. These failed supernovae produce black holes directly. The star simply dims and disappears. Astronomers have recorded such vanishings, stars observable for decades suddenly fading from existence. In each case, the simplest explanation is a direct collapse black hole. In these events, gravity does not announce its victory with fireworks. It simply pulls everything inward without resistance, and space-time curves accordingly. This type of collapse is cleaner, quieter, and more direct than a supernova, and may produce the majority of black holes in the universe. But no matter how the collapse begins, with a detonation or with silence, the final stages are governed by the same principle. Gravity bends space-time to its limit. The material that once formed the core of the star is driven inward faster than any information can escape. The collapse races ahead of all physical processes. Signals cannot travel outward fast enough to carry information about what is happening. The star's identity is erased from the outside world long before the collapse finishes. And here arises one of the deepest mysteries in physics. When gravity crushes matter beyond all possible forms, what remains? The equations of general relativity say the material continues collapsing until it forms a singularity, a point of infinite density. But infinities in physics are often signs that the theory being used has reached its limit. The singularity is not a physical object. It is a placeholder for we no longer know how to describe what's here. Quantum mechanics tells us that matter cannot compress into a point with zero volume. Some theorists suggest the collapsed matter becomes a quantum state of space-time itself. Others propose a bounce, a reversal of collapse at densities near the Planck scale. Some imagine the interior becomes a highly curved, extended region rather than a point. But whatever the true nature of the final collapse, one fact is clear. The matter falling inward creates something more important than any physical object. It creates a boundary. That boundary is the event horizon. The event horizon marks the surface where escape ceases to be possible. It is not a wall, not a layer of matter, not a solid crust. It is the location in space-time where the inward curvature becomes so extreme that all paths lead deeper. Even light cannot find a route that leads outward. Once material crosses this boundary, it disappears from the reach of the external universe. The event horizon is not the black hole. It is the outer edge of its influence, the line separating can return from lost forever. As the stellar core collapses, the event horizon forms around it, a sphere in space-time shaped entirely by the mass inside. The horizon grows as more mass falls inward. Eventually, the collapse ends, not because matter finds a stable configuration, but because space-time has redefined itself around the core. And beyond that horizon lies a structure unlike anything else in the universe, a one-way surface where gravity's triumph becomes unavoidable. When a star collapses and space-time caves in on itself, something remarkable appears. A boundary with no substance, no surface, no mass of its own, but capable of dividing the universe into two completely different realities. It is called the event horizon, and it marks the point where gravity curving space-time becomes so extreme that outward motion ceases to exist. On one side of this boundary lies the ordinary universe. On the other side lies a region from which nothing can return. But the strangest part is not the boundary itself. It is the fact that two observers watching the same fall toward this boundary will witness two stories that cannot be reconciled, yet are both correct. Imagine standing far from a black hole, watching someone drift toward it. At first, the motion seems familiar. The person accelerates, moves faster, is pulled inward the way a spacecraft would fall toward a planet. Nothing unusual appears to be happening. But as they approach the horizon, their descent begins to slow. Not because they have slowed themselves, but because the light they emit reaches you more and more delayed. The signals stretch. Every update becomes weaker, redder, and farther apart in time. Soon their movements begin to look sluggish, then suspended, as if they are sinking into a thickening medium. You watch them wave or send a signal, and the motion appears almost frozen. The color of their clothing shifts into deeper shades. Light leaving their body loses energy as it struggles to climb out of the growing gravitational depth. This stretching of wavelength, called gravitational redshift, increases not linearly, but exponentially near the horizon. The deeper they fall, the more their light is drawn out into longer wavelengths. What was once visible light drifts into infrared, then into microwaves, then into wavelengths too long for any detector to notice. Finally, even the faintest echo of their presence fades. From your vantage point, they never cross the horizon. They simply slow, dim, and dissolve into darkness, as though the universe swallowed their image without swallowing them. Now, rewind the event and view it from the perspective of the falling person. Nothing slows, nothing freezes, nothing reddens. They watch their own hands move normally. Their heart beats as usual. The horizon does not announce itself. There is no glowing boundary, no shift in gravity, no sudden sensation of passing into another region. They simply continue falling, accelerating as they approach the speed of light relative to the outside world, yet feeling none of that strain themselves. If they glance outward, they may see the universe distorted, sped up, or stretched, but their own experience remains smooth. To them, the horizon is not an event. It is just a coordinate in space-time, no different from any other location they have crossed before. This contradiction, the outside observer witnessing a perpetual freeze and the falling observer experiencing uninterrupted motion, is not a paradox to be resolved. It is the natural consequence of space-time curvature. Time does not pass at the same rate everywhere. The closer one moves toward a region of strong gravity, the slower time flows relative to distant observers. Near a black hole, this slowing becomes so extreme that the falling person's last moments are stretched infinitely long from the perspective of the outside universe. To the distant observer, the falling person never reaches the horizon. They asymptotically approach it but never complete the final step. But to the falling person, that step happens in seconds. This duality is not a mistake in reasoning. It is the structure of space-time asserting that there is no universal, absolute perspective. Clocks do not tick the same for everyone. Light does not carry information at the same pace for everyone. The horizon is a place where the difference becomes so dramatic that two observers effectively live in different realities. To understand why this happens, imagine trying to send a message from very close to the horizon. The light you send outward must climb a gravitational slope, so steep that it loses energy as it rises. In ordinary circumstances, this loss is small, but near the horizon, the slope becomes nearly vertical in the language of space-time. The energy cost becomes enormous. Eventually, the wavelengths stretch so far that the message becomes undetectable. The horizon appears dark not because anything material blocks the signals, but because all outward paths lead into infinite redshift. You can think of the horizon as a kind of one-way membrane that information cannot pass through. The falling person crosses it effortlessly because their future includes moving deeper inward. But their signals, their light, their attempts to reach back, all of these are redirected by the shape of space-time, not by force, but by geometry. The universe simply does not provide a route for those signals to escape. This is why the horizon is called a boundary of no return. If a traveler crosses it, they are not physically trapped by walls or barriers. They are trapped by the fact that space-time has become a funnel with no upward direction. Their path forward is inward, and inward is the only way time can flow for them. They move deeper not because gravity drags them, but because the geometry redefines what their future is allowed to be. For the distant observer, the horizon acts like a pause button on the traveler's existence. For the traveler, nothing of the sort happens. Both views are real within their own frames, and so, the universe gives two incompatible stories, neither wrong, both true. The horizon also explains why black holes are black, not because they gobble everything violently, but because the geometry hides everything behind an infinite redshift. Even if the falling person carried the brightest flashlight imaginable, its beam could not reach an outside observer once it was too close to the horizon. The light would stretch until it became undetectable. No signal from within can reach out. The horizon does not absorb or reflect. It erases outward communication from a region that still physically exists. The key realization is that the horizon is not the black hole. It is the edge of what the universe allows other observers to know about the black hole. Everything that remains inside may continue to evolve, move, compress, and transform. But that evolution is forever sealed off from observers in the outside universe. The horizon is the price the universe pays for allowing space-time to curve so sharply. The existence of the horizon also forces a profound question. If no signal can escape, is the region inside still part of our universe? If an object falls in and its information cannot return, does it still exist in the external sense? Does existence require visibility? Or does the interior remain just as real, even though it cannot communicate with the outside? Physics answers cautiously. The interior exists, but only for those who cross the horizon. For everyone else, events inside are not simply hidden. They are unreachable, events without meaning in the external timeline. The universe becomes partitioned. The horizon is not merely a boundary in space, but a boundary between histories. There is no shared narrative across this divide. The falling person experiences one timeline. The outside observer experiences a different one. Each timeline is internally consistent, but they cannot be unified. This leads naturally to a deeper puzzle. When the falling person crosses the horizon, they enter a region where the structure of space-time continues to collapse inward. They do not see the boundary as special, but moments later, or perhaps much later, depending on the black hole's size, they find that the rules of motion begin to warp. Directions lose meaning, space compresses, time stretches, and yet none of these features are visible from outside. The horizon not only hides location, it hides the very nature of inside. If you were falling, you might feel tidal forces tug at you, stretching you in the direction of the fall and squeezing you in the direction perpendicular to it. Or, in the case of a supermassive black hole, you might feel almost nothing at all, floating into darkness without sensation. But no signal describing your experience could ever reach back out. Anyone watching you would believe you were still hovering just above the horizon, frozen forever in red silence. This reveals a truth that is both unsettling and beautiful. The universe does not require observers to agree. The horizon is the clearest example of this principle. Two observers can witness entirely different sequences of events, with different outcomes, and the universe will accept both as valid because both arise from the geometry of space-time itself. And yet, despite all the complexity, the horizon is not the strangest part of a black hole. It is only the portal. Beyond it lies a region where the distinctions between time and space, between inner and outer, between motion and inevitability, collapse under the weight of the gravitational curvature. The horizon marks the threshold, but the interior is where the true transformation begins. Inside, time does not behave like time outside, and space does not remain space. The geometry folds in ways the outside universe cannot imitate. And deeper inside, the meaning of falling undergoes a final, irreversible change. Crossing the event horizon feels like nothing at all. There is no wall, no membrane, no sudden shift that announces you have stepped into a different domain of the universe. One moment, the world behind you still exists. The next, you have moved into a region where behind no longer has meaning. Everything you know about direction, movement, and the flow of time begins to unravel almost immediately. Not because anything violent happens at the boundary, but because the very architecture of space-time has rearranged itself around you. The horizon was never a physical object. It was a threshold in geometry. And once you pass it, geometry becomes the dictator of your future. From the outside view, your final approach seemed to stretch into eternity. But from your own perspective, only seconds have passed since you crossed the threshold. Your heartbeat remains steady. Your breathing is normal. Nothing resisted you. Nothing pushed you. Nothing tore you apart. The extreme slowing of time that an external observer witnessed does not apply to you. Your personal time, the time measured by every process inside your body, continues flowing as it always has. Only now, that time flows along a path that inevitably leads deeper inward. You cannot pause it. You cannot turn around. You cannot choose a different direction. Not because anything restrains your motion, but because the laws that structure motion have shifted. Outside the horizon, you could choose to move up, down, left, right, forward, or backward. Inside the horizon, one of those directions, the one that used to point outward, disappears from the menu of possibilities. It doesn't exist. No physical force prevents you from moving outward. The concept of outward has simply lost meaning. In its place, a new rule emerges. The direction of time and the direction toward the center are now the same. Falling inward is not something you are doing. It is something that is happening to time itself. You are not being dragged. You are being carried by the flow of your own future. This switch is what physicists mean when they say space and time exchange roles inside a black hole. Outside, space had 3 dimensions and time was the 4th. Inside, time becomes the axis pointing toward the singularity, and the spatial dimensions become distorted in ways your intuition cannot anchor to. Even if you fire your rockets, stretch your limbs, or attempt to maneuver sideways, your overall trajectory does not change. Every possible future leads deeper into the hole, as reliably as every tomorrow lies ahead of today in ordinary life. Your surroundings begin to shift, not abruptly, but noticeably. Light from the universe outside appears compressed into a shrinking patch of sky behind you. The faster you fall inward, the more the outside universe seems to speed up, as if the cosmos were playing its history at an accelerated rate. The stars you once saw slowly drifting across the sky now streak toward a single direction, merging into a bright ring of distorted light. But even that ring begins to narrow. The geometry of space-time bends the path of incoming light more sharply the deeper you fall. Soon the outside universe compresses into a thin, brilliant arc behind your back, an image you can no longer distinguish from a rapidly advancing blur. The rest of your visual field grows dark, not because there is nothing there, but because light from those regions cannot reach you in normal ways anymore. Inside the horizon, not only does your future point inward, but the paths that light can take twist. Differently from anything your brain is prepared to interpret, space is no longer laid out in familiar directions. Some directions lead toward increasing curvature, others exist only briefly before narrowing out of existence. It is as though space itself were collapsing faster than you can process it. This effect intensifies if you are inside a small black hole. The curvature of space-time near the center is so violent that tidal forces, differences in gravitational pull across your body, rise sharply. Your feet, closer to the center, are pulled more strongly than your head, while your sides are squeezed inward. The resulting stretch resembles pulling soft dough into a long, thin shape. Scientists call it spaghettification, a whimsical name for a brutal effect. It happens not because gravity is strong in the everyday sense, but because space-time is curved so extremely that distance has different meanings along different directions. The closer you get to the center, the stronger this differential tug grows until it reaches levels no physical object can survive. But not all black holes are small. If you had fallen into a supermassive black hole, 1 million or billions of times more massive than the Sun, the experience would be radically different. The curvature at the horizon of such giant black holes is surprisingly gentle. You could cross the horizon without feeling any tidal pull at all. The interior, for a while, would feel eerily smooth, like sliding into a deep lake where the surface tension never broke. You could drift for minutes, hours, or longer before the curvature intensified enough for tidal forces to matter. It is not the sudden violence often imagined in fiction. It is quiet, calm, almost peaceful, an unsettling calm that hides an unforgiving fate. Even so, the inner world remains alien. The further you fall, the more the remaining directions in space begin to narrow. Inside the horizon, space converges faster than you can physically react. If you try to hover, you only accelerate inward faster. If you try to move sideways, curvature redirects you. The black hole is not pulling you. It is reshaping the terrain beneath you so that all roads lead inward. It's like walking on a landscape where every step forward lowers you into a valley whose walls are too steep to climb. But here, the valley is space-time, and downward is merely another word for forward in time. As you descend, time around you behaves strangely. The outside universe continues to race ahead in your field of view. You watch distant galaxies whirl through millions of years in compressed flashes. Stars live, burn out, and vanish. Cosmic structures evolve and shift. All of these events play out faster than your mind can fully absorb. From your perspective, the universe you left behind is aging rapidly. To an outside observer, you are frozen. The two timelines diverge so drastically that they can no longer be reconciled. You and the outside cosmos are no longer synchronized. It is as if you inhabit a timeline that is peeled away from the rest of the universe and is now sliding deeper into its own gravitational script. This deepening curvature does not simply compress space, it distorts the rules that space follows. In a region where space-time remains stable, you can draw a straight line between 2 points and call that the shortest path. Inside a black hole, the shortest path is often not a path you can imagine. Paths bend into spirals. Some directions loop back into themselves, some shrink until they cease to exist. And one direction, the inward direction, stretches into something like a funnel, accelerating your journey toward the center even if you try to resist. At this stage, the presence of the singularity becomes unavoidable. You may not yet feel it directly, but its influence shapes every moment of your fall. The singularity is not a material object. It is not a point you can land on. It is not a physical structure sitting at the center like a seed. It is the endpoint of geodesics, the natural paths objects take when no forces act on them. Inside the horizon, your future leads inevitably toward that point. Not a destination you choose, but the end of the trail space-time provides. The singularity predicted by Einstein's equations is a place where the curvature of space-time grows without limit. Distances shrink to zero, time intervals collapse, the mathematics breaks down. But this does not necessarily mean that reality becomes infinite or that matter is compressed into an actual point. It means our current theories cannot describe what happens there. General relativity, so successful on large scales, cannot speak for what happens in the extreme interior. Quantum mechanics, so successful on small scales, cannot yet tell us how space-time behaves under gravitational collapse. The singularity is the region where these two pillars of physics overlap, and neither alone can give a full explanation. Some models propose that space-time near the center undergoes quantum fluctuations so violent that the singularity spreads out into a dense but finite structure. Others suggest that the collapse halts and rebounds, forming a bridge to another region of space-time. Others still claim the singularity is not a place at all, but a boundary where space-time ends, like the edge of a page where the text simply cannot be continued. What is certain is that no information from this region can escape back out. The horizon not only seals off light, it seals off any insight into what truly lies at the center. The interior of a black hole is a realm defined not by what we can see or measure, but by what our theories can anticipate, and where those theories fail, mystery grows. Even though the singularity remains out of reach experimentally, its presence shapes everything inside the horizon. It determines the trajectory of your fall. It determines the way space-time curves. It determines how tidal forces rise. And it determines that your journey, once begun inside the horizon, cannot be diverted. You are falling not through space, but through time directed inward. And as you approach the deepest, darkest layers of curvature, the question becomes impossible to avoid. If space-time collapses to a point, does it truly end? Or does something new begin, where our mathematics can no longer follow? A black hole born from the collapse of a massive star does not simply sit still in the darkness. The star that created it was almost certainly spinning, and the conservation of angular momentum ensures that the collapse only amplifies that rotation. Even a gentle, barely noticeable spin in the star's early life becomes a furious, unstoppable whirl once its mass is squeezed into a space smaller than a city. Rotation is not an optional feature for black holes. It is an inheritance written into the physics of collapse itself. As a result, the majority of black holes in the universe are not the quiet, static spheres imagined in simple diagrams. They are cosmic whirlpools, regions where space-time is not just curved, but twisted. To understand what this means, imagine the fabric of space-time not as a static grid, but as something fluid and dynamic. When a black hole spins, it drags space-time around with it, like a whirlpool dragging water into its swirl. This phenomenon is called frame dragging. It is not metaphorical, it is literal. The space around a rotating black hole is pulled into motion. Nothing near it, no object, no beam of light, not even the idea of standing still can escape this influence. If you drifted near a spinning black hole, you would feel this twisting not as a force that pushes or pulls you, but as a redefinition of what it means to be motionless. Even if you tried to hover with the most powerful engines imaginable, space-time itself would carry you sideways. Standing still would require moving rapidly in the opposite direction just to counteract the swirl. This effect grows stronger the closer you are drawn toward the black hole, reaching a point where the twisting becomes unavoidable. That region is known as the ergosphere. The ergosphere is one of the most striking features of a rotating black hole. It is shaped like a flattened sphere surrounding the event horizon, bulging outward at the equator where rotation is strongest. Unlike the horizon, which marks the boundary of no return, the ergosphere is a region outside the horizon where motion is still reversible, but at a price. Inside the ergosphere, space-time is dragged so dramatically that all objects must rotate along with the black hole. There is no option to remain still. The structure of space-time forbids it. From your perspective as an observer, this region would behave unlike anything in ordinary space. A spacecraft attempting to hover would find itself whipped around the black hole at incredible speeds, even as its engines struggled to compensate. Light traveling in the same direction as the rotation would be dragged forward, while light traveling against the rotation would be slowed nearly to a halt. The geometry itself is in motion, and everything within it is forced to join the dance. And yet, the ergosphere is not merely a curiosity. It has consequences that reach far beyond the black hole. Because of the way rotation twists space-time, it is actually possible for an object entering the ergosphere to extract energy from the black hole's rotation. This counterintuitive effect was discovered by Roger Penrose and is known as the Penrose process. If an object splits into two inside the ergosphere, one piece can fall into the black hole with negative energy relative to a distant observer, while the other escapes with more energy than the original object had. This is not a violation of physics. It is a consequence of how rotation reshapes the local definitions of energy and momentum. The extraction of rotational energy is one of the most fascinating demonstrations of how black holes are not just destructive, they are dynamic engines of space-time. But the twisting of space-time does not end at the ergosphere. As you fall deeper inside, crossing the event horizon of a rotating black hole, you do not enter the same interior that a non-rotating black hole would provide. The Kerr interior, named after the solution to Einstein's equations that describes rotating black holes, contains structures that have no analog in the simpler Schwarzschild case. Here, the geometry becomes layered. Horizons multiply. The path inward changes character. Instead of a single event horizon, a rotating black hole has two, an outer horizon and an inner horizon. The outer horizon acts much like its non-rotating counterpart. It marks the boundary beyond which escape becomes impossible. But the inner horizon is stranger. It is a surface where the flow of space-time becomes unstable, and where signals can, in theory, pile up infinitely. Instead of being crushed immediately by tidal forces, a traveler entering a rotating black hole might drift into a region where space-time stretches and compresses in directions that defy classical intuition. Inside a Kerr black hole, some paths might lead not directly to a singularity, but into extended regions of space-time, corridors and tunnels, mathematically speaking, that curve away from the central point. These corridors appear in the mathematics as bridges to other regions of the universe, or even to entirely separate universes. The exact interpretation is still debated. The equations allow for such structures, but whether they form in real astrophysical black holes remains uncertain. Most physicists suspect that quantum effects or instabilities would prevent traversable passages from forming. Still, the possibility encoded in the mathematics opens the door to one of the boldest ideas in theoretical physics. Rotation may be a key to creating pathways through space-time. Imagine drifting inside such a rotating interior. Instead of a straightforward plunge toward the center, your path bends into spirals and loops. The fabric of space-time beneath you is not collapsing uniformly, but swirling, folding, and elongating. Some directions appear to stretch into tunnels, others close off. Your sense of direction becomes unreliable, not because your body is spinning, but because the coordinates of the universe itself have become warped by rotation. And then there is the singularity, not a point, as in the non-rotating case, but a ring. In the Kerr geometry, the singularity is a spinning ring of extreme curvature, not a single puncture in space-time. This ring singularity, at least mathematically, allows paths that might pass through it to regions on the other side. In idealized models, these paths can lead to new sheets of space-time entirely disconnected from the universe outside the black hole. But before imagination leaps too far, reality pushes back. Most physicists believe the inner horizon is unstable. The slightest disturbance, any particle, any fluctuation, any ripple in space-time would amplify catastrophically, overwhelming the structure predicted by the clean mathematical solution. Under real astrophysical conditions, the neat traversable tunnels of the Kerr interior likely collapse into something chaotic and violent. The ring singularity may not remain open to passage. Instead, it may destabilize and crush everything that enters. Yet the possibility remains part of the mathematics, and mathematics often reveals truths about the universe long before experiments can confirm them. Black holes have a history of surprising us. They were dismissed as mathematical oddities for decades before observations proved they were real. The Penrose process was once considered improbable until astrophysical jets, streams of energy launched from spinning black holes, showed that nature indeed extracts rotational energy from them. The twisting of space-time was once theoretical. Now it has been measured around Earth itself by gravity probe missions. So the idea that rotation might allow deeper structures within black holes cannot be ignored. Even if no traveler can survive the journey, and even if no wormhole opens cleanly, studying the interior of rotating black holes forces physicists to confront the limits of general relativity and the need for a deeper understanding of quantum gravity. It also offers a reminder that black holes are not simple voids. They are dynamic systems with rich internal architecture. If you were falling into a rotating black hole, your subjective experience would depend strongly on where you entered. Approaching along the axis of rotation would lead to a very different descent than approaching at the equator. In some directions, tidal forces might rip you apart quickly. In others, space-time could feel eerily smooth, carrying you inward along curved paths. Near the ergosphere, you would be swept into rotation, whether you wanted to or not. Deeper inside, as you pass the inner horizon, the strange strengthening and weakening of gravitational fields could disorient you, bending your sense of momentum and twisting the very meaning of direction. The center would not feel like a point. It would feel like a pull built into time. Every step of this descent raises new questions. How stable is the inner horizon? Can space-time really stretch into corridors? Does the ring singularity have a physical reality? If rotation changes the interior structure so drastically, what other surprises could be hidden at the limits of our understanding? Even before these questions are answered, one truth stands out clearly. Rotation is not a detail. It is a fundamental part of what makes black holes extraordinary. It deepens their curvature. It twists their geometry. It shapes the regions around them into landscapes where energy can be extracted, where light is compelled to spiral, and where the interior might expand into shapes no human has ever experienced. Rotation adds a new dimension to black holes, not just physically, but conceptually. If twisted space-time can create corridors, even fragile or unstable ones, then perhaps the black hole is not the end of a journey, but the beginning of a possibility. For centuries, physics has carried a quiet confidence. The universe keeps perfect records. No matter what happens to an object, whether it burns, breaks, dissolves, or scatters, the underlying information about what it once was can never be truly destroyed. Quantum mechanics treats this as sacred. Processes may scramble information, stretch it, hide it, or smear it across space, but they never erase it. The universe remembers everything, but black holes seem to disagree. A black hole swallows matter without a ripple. Stars, planets, dust clouds, radiation, and every bit of structure encoded in them vanish behind the horizon without revealing what becomes of them. From the outside, the horizon is silent, smooth, and indifferent. It does not twist or bulge or glow with the details of what has fallen inside. And if the black hole were to remain unchanged, if it stayed black forever, then perhaps this silence would be tolerable. The information would be inaccessible, but not necessarily lost. But black holes do not remain unchanged. They do not stay silent forever. In the 1970s, Stephen Hawking discovered a phenomenon that transformed black holes from eternal prisons into objects that gradually evaporate. His insight did not come from general relativity, which portrays black holes as perfect absorbers with no means of escape, but from quantum mechanics, the physics of fields, particles, and the restless fluctuations that fill the vacuum. According to quantum theory, empty space is never truly empty. It is filled with pairs of virtual particles that appear and vanish too quickly to be directly observed. These pairs normally annihilate each other almost immediately, but near a black hole's horizon, the rules change. Imagine such a pair forming right at the boundary, where the curvature of space-time is intense. One particle falls inside, the other escapes outward before the pair can annihilate. From the outside observer's point of view, that escaping particle looks like radiation, real radiation. And because energy must come from somewhere, it comes from the black hole itself. With each emitted particle, the black hole loses a tiny amount of mass. Over astronomical timescales, this process causes the black hole to shrink. Eventually, after emitting enough radiation, it disappears entirely. This radiation is now known as Hawking radiation, and its discovery created one of the biggest crises in theoretical physics. If a black hole evaporates completely, what happens to the information about every object that fell in? Quantum mechanics insists the information must survive. General relativity insists the black hole destroys it. Both theories are extraordinarily successful. Both are backed by mountains of evidence, but they cannot both be right. The paradox has a simple statement and an impossibly deep implication. If Hawking radiation contains no information about what fell in, and the black hole eventually evaporates, then information has been lost forever, something quantum mechanics claims cannot happen. At first glance, Hawking's calculation seems clear. The radiation that escapes looks thermal, pure heat, containing no imprint of the matter that created it, no variation, no structure, no hint of what the black hole consumed, just featureless radiation. If this is true, then black holes erase information from the universe. But the deeper one looks, the stranger the situation becomes. Even before Hawking radiation was discovered, physicists realized that black holes behave like thermodynamic objects. They have entropy, a measure of how many possible internal states they could have. But unlike ordinary objects, whose entropy scales with their volume, a black hole's entropy scales with the area of its horizon. This is an almost shocking clue. It means the information capacity of a black hole might be encoded on a two-dimensional surface, not in its three-dimensional interior. If that is true, then the horizon is more than a geometric boundary. It is a storage device. This idea, first suggested by Einstein, seemed absurd at the time, but the math was unmistakable. The amount of entropy in a black hole is enormous, and it is proportional to the square of its radius, not to the cube. Something about black hole physics respects surface area rather than volume. It is as though the horizon functions like a cosmic hard drive. Its surface encodes everything that has ever crossed it. But that only deepens the mystery. If the information is encoded on the surface, how does it survive evaporation? Does Hawking radiation somehow carry the information out in a scrambled form? Or does the horizon store information until the very last moment and then release it in a final burst? Or does the information leak out gradually, hidden in correlations too subtle for Hawking's original calculation to detect? The proposals multiplied. One idea, called black hole complementarity, suggests that both descriptions, the external observer seeing information stored on the horizon and the falling observer seeing information pass inside, are true but cannot be compared directly. No observer can see both realities at once, and the universe ensures the contradiction does not lead to measurable inconsistency. This is elegant but fragile. It depends on the assumption that the horizon behaves like a smooth surface for someone falling through. Another idea, the firewall hypothesis, challenges that assumption directly. According to this radical proposal, the horizon is not smooth at all. Instead, it is a wall of high-energy radiation, a firewall that destroys anything crossing it. If this were true, the information would be preserved on the outside surface of the black hole, and the interior would not meaningfully exist. But this solution comes at a cost. It destroys the very essence of Einstein's equivalence principle, a foundational idea of general relativity. Most physicists are reluctant to accept this sacrifice without extraordinary evidence. A more subtle approach suggests that information is not lost, because Hawking radiation is not purely thermal after all. According to this view, the outgoing radiation contains correlations, patterns too subtle for Hawking's first computation to detect, which carry information outward. Over the long lifetime of a black hole, these correlations build up gradually until the information is fully released. This is consistent with quantum mechanics, but requires a complex restructuring of how horizons work. The deeper physicists investigate, the clearer it becomes that the paradox is forcing a kind of confrontation. General relativity describes the horizon as a perfect one-way membrane. Quantum mechanics demands that it be, in some hidden sense, a two-way accountant, keeping track of everything that passes. The two views collide at the horizon, and neither theory on its own can resolve the contradiction. This deadlock has led many to suspect that the paradox is not a flaw but a clue. Perhaps the horizon is not a literal surface, but a holographic boundary, a storage layer encoding the interior as if on a screen. Perhaps the interior is not a volume, but a projection from this boundary. Perhaps the information that seems to vanish inward is never inside at all, but encoded on the edge of the black hole in a form only quantum gravity can decipher. This radical possibility, first hinted at by the behavior of black hole entropy, has grown into one of the most influential ideas in modern theoretical physics. And yet, despite decades of debate, no single resolution has been universally accepted. Each proposed solution repairs one part of the paradox only to strain another. This is why the information paradox remains one of the largest unresolved problems in science, not because the mathematics is unclear, but because the paradox exposes the limits of our two greatest theories. Black holes are where general relativity and quantum mechanics speak at full volume, and both refuse to stay silent. They tell different stories that cannot coexist unless there is a deeper, unifying framework beneath them. The information paradox is not a puzzle about bookkeeping. It is a doorway to the next layer of physics. If information truly lives on the horizon, then the interior of a black hole might not be what we think. And if the universe itself respects a similar rule, where information is stored on a cosmic boundary, then the world we inhabit may be a kind of hologram, a three-dimensional experience encoded on a two-dimensional surface. The horizon, once a simple boundary, may be the first hint that the universe does not operate in the number of dimensions we perceive. The paradox of information forces physics to stare at a possibility that once seemed unthinkable. Maybe the universe does not store its information in the volume of space at all. Maybe it stores it on surfaces. A black hole, quiet and opaque, offers this possibility in its most dramatic form. Its entropy, the measure of how much information it can contain, doesn't depend on how much space lies inside it, but only on the area of its horizon. It is as if the boundary knows everything, and the interior is a kind of illusion the boundary produces. At first, this sounds abstract, even mystical, but it may be the most grounded, testable idea about the universe we have ever stumbled upon. To understand how shocking this is, consider a hologram in the ordinary world. A hologram is nothing more than a thin, flat surface. When you look at it from the side, it offers no depth, no shape, no hint of a world inside. And yet, under the right light, the surface produces the illusion of a three-dimensional scene. Mountains appear to rise, faces seem to rotate, objects occupy space they do not physically possess. The depth you see is not contained in the volume of the hologram. It is encoded in the variations of light recorded on its two-dimensional surface. The insight of holography is simple, but revolutionary. You can represent a world of three dimensions using patterns etched onto a world of two. What if nature uses the same trick? Black holes were the first hint. When researchers like Bekenstein and Hawking realized that the entropy of a black hole scales with its surface area rather than its volume, something profound came into view. Every other object in physics stores information in proportion to its volume. Double the size of a box, and you can double the amount of stuff you can put in it. But a black hole does not behave like a box. Its information capacity grows with its surface, the area of its horizon. If the horizon doubles its radius, its surface area grows fourfold, and so does its entropy. The interior might be enormous, but the interior contributes nothing to the entropy directly. Only the boundary matters. This is not an optional detail. It is a strict mathematical fact. And it means that the horizon is playing a role no ordinary surface plays. It is more than a location. It is a storage layer. Where it writes its information and how it writes it remain mysteries, but the effect is unmistakable. This idea soon expanded beyond black holes. If a black hole stores all its information on the horizon, could the entire universe store its information on its cosmic boundary? Could space itself, the three-dimensional expanse we move through, be a kind of projection of information encoded elsewhere? Imagine that everything you see, every object you touch, every distance you measure, emerges not from the interior of space, but from a deeper, two-dimensional structure. Imagine that your experience of depth is similar to the depth you perceive in a hologram, real to your senses, but created by underlying patterns living on a surface you never directly see. At first, this feels like science fiction, but physics has a habit of turning once outrageous ideas into reliable tools. The most famous demonstration of holography in theoretical physics is the AD-S-CFT correspondence, discovered by Juan Maldacena in 1997. Although the details involve advanced mathematics, The core message is beautifully simple. A complete description of a universe with gravity in 3 dimensions can be equivalent to a description written entirely on its 2-dimensional boundary, where gravity does not appear at all. In other words, you can describe everything happening inside a volume by describing information on its surface. This astonishing duality brings the holographic idea into sharp focus. It suggests that space, gravity, and even the dynamics of matter might be emergent phenomena, shadows cast by something deeper and simpler. The AD-S-CFT correspondence is highly specific. It applies to a universe with certain properties and is not directly our universe, but it proves a principle that was once unimaginable. It shows that nature can encode a volume on a boundary. Black holes reinforce this again and again. When something falls inside a black hole, the information about it does not simply vanish. According to holography, the horizon absorbs and encodes that information in some form, stretched out across its surface like a cosmic ledger. The interior then becomes a kind of reconstruction of those boundary states, the way a 3D image emerges from the 2D patterns etched onto a hologram. In this view, the singularity at the center of the black hole might not be a literal point where physics breaks down, but the result of trying to interpret 3-dimensional geometry too literally, ignoring its boundary-based origin. This perspective begins to weave a consistent picture from threads that once contradicted each other. In classical general relativity, the interior of a black hole is a real physical region that objects fall into. In quantum mechanics, information cannot be lost and must remain accessible somewhere. In holography, both interpretations can be true, because the interior is like a projection generated by the information stored on the horizon. What happens inside is encoded outside, and the apparent contradiction dissolves. To see how radical this is, imagine a book. In the conventional view, the story is contained inside the pages, in the volume of the book itself. But in a holographic view, the entire story could be encoded on the surface of the cover alone, and the pages are something like a generated illusion. Removing the pages would not remove the information, only erasing the surface would. This also offers a new lens on the information paradox. If all the information of a black hole lives on its horizon, then Hawking radiation may be able to carry it out in disguised form. Everything that ever fell into the black hole is written somewhere on the boundary, and as the surface shrinks through evaporation, the information encoded on it could return to the universe in a scrambled but complete way. The black hole's interior would never have been the true home of the information. It would have been an emergent space, a kind of elaboration of the data living on the horizon. In this sense, the universe we inhabit might work similarly. Our 3-dimensional experience, distance, volume, shape, could be an emergent expression of information living on a cosmic boundary. If black holes obey holography, and if the universe contains cosmological horizons of its own, then perhaps our entire cosmos participates in a holographic pattern. Your body, the room around you, the earth beneath you, the galaxies spinning in the night sky, all could be encoded on a boundary far beyond your reach. But this does not mean the world is an illusion or a simulation. A hologram is real in its own way. It has structure, laws, and behavior governed by precise rules. The 3-dimensional image it generates is no less meaningful because it is derived from a 2-dimensional source. Likewise, if our universe is holographic, the space we live in is not fake. It is an emergent layer of reality built on a deeper foundation. Holography does not make the world unreal. It makes it profoundly interconnected. The idea becomes even more compelling when you consider what lies inside black holes. The interior, warped, collapsing, and extreme, might be a transformed representation of the data on the horizon. The singularity might be more like a coordinate breakdown in that representation than a physical point where matter accumulates. And if so, then the classical picture of falling into the center becomes less literal. The interior becomes a dynamic manifestation of how information flows on the horizon the same way. The image in a hologram is shaped by the structures encoded on its surface. This raises a deeper question. If the interior of a black hole is a holographic construction, what about the interior of the universe itself? Our cosmos has a horizon, the boundary beyond which light has not yet had time to reach us since the Big Bang. If information in black holes is stored on horizons, could information in the universe also be stored on this cosmic horizon? Could the entire observable universe be the holographic projection of quantum processes happening at the edge of space-time? This idea has not been proven, but it finds support in surprising places. Some models of cosmology suggest that the large-scale structure of the universe, the distribution of galaxies, the ripples in the cosmic background, the dynamics of expansion, carry signatures consistent with holographic encoding. It is too early to say whether these signatures are more than hints, but the possibility has changed how physicists think about space. Holography is not just a mathematical curiosity. It is a bridge between gravity and quantum mechanics, a framework that can accommodate horizons, singularities, and information without contradiction. It offers a picture of reality where the inside and the outside of a region are not separate but intimately linked. And it suggests that the most important structures in the universe might live not in volumes, but on surfaces. Black holes, once thought to be the most opaque objects in the cosmos, suddenly appear as windows into a deeper layer of reality. Their horizons behave like the screens of cosmic devices, storing and projecting the information that defines everything that falls inside. If this perspective is right, then the universe becomes an intricate web of surfaces and projections, where information creates space, and space creates the experience of depth. The world we move through each day might be less like a room, and more like a story written on a boundary, and this yields a final, remarkable possibility. If black holes encode universes on their surfaces, and if holography is a fundamental principle of nature, then perhaps our entire cosmos is the interior of a black hole in some larger reality. A vast holographic projection emerging from a boundary we will never see. The holographic principle invites a radical possibility that a black hole does not merely swallow information, but transforms it into the seeds of something new. And once that idea appears, another follows almost automatically. If a black hole can encode the information of everything that fell into it, and if its interior is not simply a point of destruction, but a region with its own space-time geometry, then perhaps the interior is not an end at all. Perhaps it is a beginning, a place where space opens instead of collapses, a place where the story resets itself. This leads to one of the boldest claims in modern cosmology. Our own universe might have been born inside a black hole. To understand why physicists take this seriously, imagine the interior of a black hole not as a collapsing funnel that narrows to nothing, but as a region where curvature becomes so extreme that space and time undergo a phase change. In classical general relativity, this collapse ends in a singularity, a point of infinite density where all description breaks down. But quantum mechanics refuses to accept infinite anything. At incredibly high densities, quantum effects create enormous pressure. Instead of letting space-time compress indefinitely, this pressure can cause a bounce. Collapse slows, the inward rush halts, and then the geometry turns outward again. To a distant observer, nothing of this bounce is visible. All they ever see is matter vanishing past the horizon and a silent black hole remaining. But from the viewpoint of the matter inside, the collapse may reverse. Instead of ending at a singularity, the interior may undergo an expansion, a rapid, violent, accelerating expansion that to any inhabitant inside would look like the beginning of a universe. A beginning very much like the Big Bang. This is the core idea behind Nikodem Popovsky's black hole cosmology model. In this view, every black hole in our universe contains, on the other side of its interior collapse, a new expanding region of space-time, a daughter universe. What we call singularity is not a point, but a transition. A doorway between a collapsing parent universe and an expanding child universe. The Big Bang is simply the moment when the bounce occurs. The new universe comes into existence not out of nothing, but out of the crushed remains of a previous cosmic environment. Loop quantum gravity, a framework that quantizes space-time itself, supports this idea. When space-time is treated as a granular structure, not infinitely divisible, its curvature cannot grow beyond a certain limit. Once that limit is reached, collapse transforms into expansion. Singularities vanish, replaced by bridges of extreme curvature, where one universe can give birth to another. In this sense, every black hole is not a grave, but a womb. But even without loop quantum gravity, classical cosmology carries a hint of this structure. Our universe, on the largest scales, is described by the Friedmann-Robertson Walker, FRW metric, A collapsing black hole interior is described by a different but surprisingly related metric. In fact, the mathematics describing the interior of a black hole has expansions that resemble the equations governing our own universe. Both involve rapidly changing curvature, a tightly packed early state, and a transition into expansion. Both describe spacetime evolving outward from an incredibly dense beginning. Even more striking is the behavior of horizons. A black hole has an event horizon, a boundary that hides everything inside from the outside universe. Our universe has a cosmic horizon, a boundary beyond which light has not had time to reach us since the Big Bang. In both cases, the observable region is sealed by a horizon beyond which no information is accessible. In both cases, the geometry is shaped by energy density and expansion. And in both cases, the horizon's area encodes information. The parallels are almost eerie. If you were inside a universe born from a black hole, the parent universe would be forever inaccessible to you. You would see your own cosmic horizon, but never the world beyond it. You would measure your universe expanding, cooling, forming galaxies and stars, unaware that its origin lay on the other side of gravitational collapse. From your perspective, your universe would appear self-contained, smooth, and uniform, exactly as ours does. In fact, the uniformity of our universe is one of the strongest hints in favor of this idea. The cosmic microwave background, the faint afterglow of the Big Bang, is astonishingly smooth across the sky. Regions that should never have been in contact with each other appear to have shared the same temperature and density at early times. Cosmologists call this the horizon problem. Inflation theory attempts to solve it by proposing a brief era of exponential expansion. But the black hole-born universe has an alternative explanation. Before the bounce, the matter that formed our universe was compressed into a tiny region inside the parent universe's black hole. It had ample time to homogenize before expansion began. No extra inflation is needed to explain the smoothness. Another clue is angular momentum. Our universe, on the largest scales, does not appear to be rotating. That is exactly what you would expect if our universe were formed inside a supermassive black hole in a larger cosmos. The interior geometry of a non-rotating or slowly rotating black hole naturally produces a universe with negligible large-scale rotation. The initial conditions of our cosmos, once treated as arbitrary, look suspiciously like the predicted conditions inside certain types of black hole interiors. Even the flatness of our universe, the puzzling observation that space is almost perfectly balanced between expansion and collapse, fits more cleanly into a black hole origin story than into traditional Big Bang models. The critical density required for flatness emerges naturally from the geometry inside a collapsing region that rebounds into expansion. And yet, even with all these hints, the idea remains speculative. For one thing, we cannot observe the parent universe directly. Even if our universe is a black hole interior, its horizon is not a boundary we can cross. It is the cosmic horizon, the limit of what we can see due to the finite age of the universe. The parent universe, if it exists, lies beyond an opacity we will never penetrate. Still, the models are internally consistent. They fit the mathematics. They fit the geometry. And the more physicists explore the structure of black holes, the more appealing the idea becomes. A universe born inside a black hole is not a fanciful story. It is a natural implication of ideas we already accept, that information cannot be destroyed, that space-time is dynamical, and that singularities signal missing physics rather than literal infinities. Of course, this idea also raises unsettling questions. If our universe was born from a black hole, who or what created the black hole that birthed us? A massive star in some grander cosmos? A collapse of matter we cannot imagine? A cycle of universes, each giving rise to the next through black holes in an infinite chain? And if our universe contains countless black holes of its own, are they each producing daughter universes? Does every black hole hold a new cosmos behind its event horizon? Could those universes produce black holes that produce universes in turn? The picture grows vast very quickly. Instead of a single universe, there may be a branching tree of universes, each with its own laws of physics shaped by the conditions of its birth. The idea becomes a cosmic genealogy, a family tree of universes spreading outward through endless gravitational collapses. And that brings the most profound question of all. What does it mean if our universe is not the universe, but merely a universe, one leaf on an unimaginably large tree? What does it mean if the place we call everything is just the interior of a structure in another, larger world? Physics does not yet have the tools to answer this, but it can show us the shape of the question. And the shape of the question suggests that the end of a universe is not truly an end. When a black hole forms, it may not be closing the book on a star's life. It may be writing the opening line of a cosmos. A black hole can swallow stars whole, bend the paths of galaxies, and reshape space-time with nothing more than its presence. It can survive supernova blasts, endure collisions, drift across cosmic wilderness, and persist for longer than any other known object. It is, in almost every sense, the most durable structure the universe can produce. And yet, for all its power, a black hole is not immortal. It has a lifespan. It has an ending, and its ending is unlike that of anything else in the cosmos. The strange truth is that a black hole dies not in a cataclysmic roar, but in a whisper, a faint thermal glow that slowly, relentlessly, steals its mass away. To understand how something so massive can evaporate, we return once more to the quantum world. Empty space, far from being truly empty, swarms with fleeting pairs of particles and antiparticles. These pairs normally appear and annihilate in an instant, unnoticed and harmless. But near the event horizon of a black hole, their dance takes a different turn. If one particle falls inward while the other escapes outward, the pair never reunites. The escaping particle becomes part of what we call Hawking radiation. And with each particle that escapes, the black hole loses a tiny amount of its mass. This process is unimaginably slow. A black hole formed from a star, say 10 times the mass of the Sun, would take around 1067 years to evaporate. That is a number so large it dwarfs every other timescale in cosmic history. The universe today is only about 110 years old. A stellar mass black hole will outlive the stars, the galaxies, and even the atoms that make up matter as we know it. Long after starlight fades and galaxies fall silent, long after protons decay, if they do, black holes will still remain, silently radiating. The largest black holes, true titans like TON 618, weighing billions of suns, live even longer. They will survive for roughly 2,100 years. That is a timescale beyond intuition, beyond imagination. It is not merely another chapter in cosmic history. It is a future era so far removed from the present that our current universe will be as ancient to that epoch as the first microseconds after the Big Bang are to us. In this distant future, the universe will be dark. Stars will have burned out. Matter will have thinned. Galaxies will have drifted apart until nothing binds them. And in that darkness, black holes will be the last sources of warmth, tiny, faint, but persistent. Yet, as black holes lose mass, their temperature rises. This is the opposite of what we experience in everyday life. When a hot object cools down, it emits radiation and becomes colder. But a black hole becomes hotter as it emits radiation. The smaller it gets, the more rapidly it evaporates, and the faster its temperature rises. A stellar mass black hole today might be colder than the cosmic microwave background, but in its final seconds, it will reach temperatures high enough to glow with bursts of energetic radiation. What began as the most powerful gravitational object in the universe ends as a flash of heat. One last outburst as the horizon shrinks to nothing. But this evaporation raises a profound question. If a black hole eventually disappears, what happens to the information of everything that fell inside? Where do the details of swallowed stars, planets, atoms, and radiation go? Hawking radiation appears thermal, devoid of structure, suggesting that the information is lost forever. Yet, quantum mechanics insists information cannot be destroyed. The contradiction creates a tension that physics has not yet resolved. If the universe were to watch the evaporation from afar, it would see the black hole fade, shrink, and finally evaporate completely. But nothing in this view indicates where the information has gone. Is it encoded in subtle correlations between the emitted particles? Does it remain on the horizon, released only at the end? Or does the horizon itself act as a kind of holographic storage device, preserving all the information and imprinting it onto the outgoing radiation? Now, imagine applying this logic on a cosmic scale. If our universe is, as some models propose, the interior of a black hole inside a larger, parent universe, then its entire existence is tied to the fate of that parent black hole. From the outside, in the parent universe, our cosmic history might unfold in an instant. The expansion of our universe, the billions of years of evolution, might correspond to a moment of internal bounce inside the collapsing star of the parent cosmos. Our universe's vast timeline could fit entirely within the finite evaporation time of the black hole that birthed it. So, what happens when that black hole reaches the end of its life? Does the evaporation of the parent black hole correspond to the far future death of our own universe? Or is the interior universe, ours, so causally disconnected that the parent's evaporation has no effect on us? Could the end of one horizon mark the beginning of another? One compelling possibility is that the heat death of our universe, the era when energy is evenly spread, when motion ceases, when temperature approaches absolute zero, mirrors the slow evaporation of the black hole that surrounds us. If our universe is a black hole interior, its ultimate fate may be tied to the slow decay of its parent. The horizons shrink. The stored information is gradually released. Space thins, energy diffuses, structures dissolve, and what is left is a faint, ephemeral whisper of heat. Then nothing. But even that nothing demands interpretation. What truly remains when the last black hole evaporates? Does space-time itself dissolve, leaving behind no geometry, no field, no vacuum? Or does the final burst of radiation contain all the information that was ever stored inside, unleashed in a cosmic exhale? Or is the end of a black hole simply the signal of a deeper transition, the beginning of something new? If black holes can give rise to universes and black holes can die, then perhaps the death of a black hole is not an erasure, but a rebirth, a transfer of information from one phase of reality to another, a handoff between generations of universes in an endless chain of collapse and expansion, contraction and creation. But this possibility invites another. If the universe is a sequence of transformations, not a static object, then perhaps meaning lies not in beginnings or endings, but in the patterns that connect them. As black holes evaporate, they leave behind a mystery that refuses to lessen. The deeper physicists dig into the nature of black holes, their formation, their interiors, their rotation, their holography, their evaporation, the more black holes appear not as anomalies of spacetime, but as its most fundamental expressions. They are places where the rules of reality reach their limits. They are mirrors showing us what physics will become when it grows beyond its current form. Black holes began this journey as shadows on the edge of understanding, strange, silent regions, where light vanished and equations spiraled toward infinities. But after tracing their structure layer by layer, after standing at their horizons, and imagining their interiors after following their rotations, their paradoxes, their holograms, their collapses and evaporations, something becomes unmistakably clear. Black holes are not anomalies. They are the most honest expressions of the laws that govern our universe. They are the places where those laws reveal what they truly are when nothing prevents them from reaching their full strength. The ordinary world gives us softened versions of physics, gentle gravity, mild curvature, time that flows evenly, space that feels stable. Black holes strip away the moderation. They show us gravity at absolute scale. They show us quantum mechanics confronting space-time. They show us what happens when the universe applies its own rules without compromise. In that sense, black holes are not the breakdown of physics. They are physics in its purest form. At the boundary of a black hole, general relativity bends the trajectory of light so severely that outward motion becomes impossible. At the same boundary, quantum mechanics produces the faint thermal glow that eventually causes the black hole to evaporate. The horizon is therefore not simply a surface, it is the meeting point of two great physical languages. One describes geometry, shaping the cosmic stage. The other describes information, shaping the actors who move upon it. Both speak with equal authority. Both make incompatible demands. And at the horizon, both must be true. No other environment in the universe forces physics to declare its contradictions so openly. And yet, black holes also reveal harmony. The entropy encoded on their horizons hints at a deeper unity between information and geometry. The holographic principle dissolves the apparent contradiction between inside and outside. Hawking radiation whispers that information must find a path back into the universe, even when the horizon seems determined to hide it. These are not fragments of a broken theory. They are trail markers, signposts pointing toward a more complete understanding of nature that lies beyond both general relativity and quantum mechanics. But black holes are not merely arenas for exotic physics. They are also architects of the universe. At the centers of galaxies, supermassive black holes regulate the birth of stars, shape the distribution of matter, and distribute energy across vast cosmic webs. Their jets sculpt interstellar gas, seed heavy elements, and ignite new stellar generations. Without black holes, galaxies would look different. Star formation would proceed differently. The large-scale structure of the universe itself would be altered. Black holes do not threaten cosmic order, they create it. This paradox, objects that destroy locally but build cosmically, is one of the clearest signs that black holes are woven into the universe's natural design. Their gravity anchors galaxies. Their energy outputs ignite matter. Their collapses may generate new universes. They are not intruders. They are pillars. And deeper still, black holes function as maps. Each feature we have explored, dense collapse, the horizon, time dilation, space-time inversion, rotation, ergospheres, inner horizons, holography, evaporation, reveals a layer of space-time's architecture. They show us that time is flexible, that space can twist, that geometry can encode information, that horizons can act as cosmic storage devices, and that the universe respects deeper principles than the ones our senses reveal. To understand black holes is to understand what space-time is capable of. Without them, our understanding of reality would be flatter, smaller, and incomplete. Black holes also force us to consider the possibility that our universe is not singular. If a collapsing star can create a new universe, and if every black hole might contain an expanding region behind its horizon, then the cosmos is not a lone island. It is an archipelago, perhaps an infinite one, in which universes give rise to universes across generations of gravitational collapse. Each black hole becomes an umbilical cord connecting one cosmos to another, and each universe becomes the interior of a black hole in some larger, older world. This possibility, though speculative, is grounded in real physics. The mathematics of black hole interiors resembles the mathematics of our expanding universe. Loop quantum gravity transforms singularities into bounces. Holography encodes volumes on surfaces. Entropy rules make horizons computational engines. Together, these ideas sketch a picture in which universes may exist, nested within universes, each connected by the geometry of collapse and expansion. If this picture is accurate, then our universe's Big Bang is not the origin of everything, but the continuation of something older. And inside our own universe, every black hole may be performing the same generative act, creating new cosmic regions we will never see. Reality becomes not a single story, but a branching tree, an ever-growing network of beginnings and endings, each linked through the physics of horizons. And this brings us to the final, unavoidable question. If everything in a black hole is encoded on its surface, if the interior is an emergent expression of the boundary, then what does that make our own experience? Are we living inside a volume or inside a projection? Is our world the inside of some higher dimensional boundary we cannot perceive? If information is the foundation of existence, then perhaps matter, energy, and even space-time are expressions of something deeper still, patterns of information that reality arranges into the structures we call the universe. Yet none of these ideas diminish the experience of living within this universe. A holographic world is still a real world. An emergent space-time is still space-time. What changes is our sense of position, our place in a much larger story. Black holes invite us to see that story not as linear, but as layered, not as closed, but as open, not as fixed, but as evolving across scales vastly larger than we can observe. As we step back from the details and allow the entire picture to settle, we begin to sense the elegance beneath the complexity. Black holes embody every aspect of the physical world: gravity's curvature, quantum mechanics probability, thermodynamics irreversibility, information theory's precision, cosmology's vastness, geometry's flexibility. They are not exceptions, they are syntheses. Their existence means the universe must be capable of unifying everything we know and everything we do not yet understand. And that unity is not just abstract, it touches the nature of existence itself. If black holes can store information, then information matters. If horizons can behave like surfaces of reality, then boundaries matter. If singularities transform collapse into expansion, then beginnings and endings matter. Black holes teach us that nothing is isolated, not particles, not stars, not galaxies, not even universes. Everything is connected through deeper principles that govern how matter curves spacetime and how spacetime records its own history. Black holes are not cosmic monsters, they are cosmic mirrors. When we look at them, we see not only the extremes of physics, but the structure of the universe reflected with startling clarity. They reveal a world where space and time are flexible, where information is conserved, where horizons shape what we can know, where matter and geometry are interchangeable, and where reality may be far larger than the universe we observe. Black holes don't end stories, they begin them. Everyone might birth a universe. Everyone transforms rather than destroys. And if that's true, then what is our universe inside of? What black hole gave birth to us? What structure holds the stage we're standing on? Physics can't answer that yet. We're left suspended between what we know and what we can only imagine. But that's not a weakness. That's the edge where science happens. Sleep well.